Hello, I'm Sally Kornbluth, president of MIT, and I'm thrilled to welcome you to my podcast, Curiosity Unbounded. This podcast is your chance to join me as I talk with pioneers who are pushing the frontiers of knowledge and inventing real-world solutions for a better future. Today, my guest is Song Han. Song is an associate professor of electrical engineering and computer science at MIT, whose research focuses on boosting the efficiency of AI computing. He develops techniques to shrink and speed up large AI models, cutting their energy use, lowering their cost, enabling them to run faster on everything from cloud servers to personal devices. His work has advanced high-resolution computer vision for autonomous vehicles, led to more efficient AI image generation, improved GPT performance, and yielded new methods for training machine learning models. All things we're thinking about, all things that are in the news all of the time. And if our listeners are like me, all things they're incredibly curious about. So, Song, welcome to the show.
Thank you, Sally. I'm very honored to be here. Excited to talk about efficient AI stuff.
Excellent. So what first inspired you to make AI models more efficient?
Actually, that dates back to a decade ago when I was doing PhD at Stanford. We were trying to accelerate large neural networks with my advisor, Professor Bill Daly. And initially, we were trying to use the hardware solution to build accelerators for that. And we actually find before we do hardware acceleration, there's a huge opportunity to actually shrink these models from the software perspective, make it a lot smaller, lower memory footprint before you can do hardware acceleration. And then we can design specialized hardware to accelerate a small and compressed model to combine the efforts from software and hardware to do this co-design and make it a lot smaller and a lot more efficient.
You know, it's interesting. The first time I heard you talk about this was right after DeepSeek came out. It was DeepSeek, is that what was it called? That hit the news.
Yeah.
And you came and talked, I think, to some leadership about it. And I think we all thought that there was some revolution in technology, but it was actually sort of an optimization of many different elements. So what's happening under the hood for the large AI systems that makes them so energy intensive? And how do you think about compression? In other words, what are the elements of compression?
Yeah. So actually, there are two reasons why it's so energy consuming. One is compute. One is data movement. So these large neural networks require a lot of arithmetic compute. So they require a lot of energy for that perspective. And secondly, moving the data is even more expensive, including moving the weight, the activation, the KV cache, moving it from machine to machine, GPU to GPU, memory to cache is even more expensive. So those are the two reasons. And model compression can improve the efficiency because it can not only reduce the model size, but also it shrinks the amount of arithmetic compute and also reduce the amount of data movement. So you get this compound benefit for saving the energy.
So there's a lot of details in the large models that are maybe nice to have, but not essential for AI to function. Is that correct? And so you're actually sort of eliminating data in a way when you compress?
Oh yeah, exactly. That's the motivation where we find that's called pruning, where pruning a neural network is like pruning a tree, where you have so many branches, some of that on the trunk, you cannot prune it. Some of them are like side branches. You can remove them safely without hurting the accuracy, without hurting the tree. Similar for neural networks, we can prune it at different granularity. Also, we can quantize it rather than using a full precision, like 32 bits to represent a number. We can use only 8 bits or even 4 bits to represent a number. And finally, we can use distillation techniques, having a large model teach a small model so that the small model can learn from the large model and get to a closer accuracy as the larger model so that we can use a small model in production, in practice.
I see. So, it said, when I was introducing you, I mentioned your interest in sort of image generation. Is it much more difficult to compress image generation AI than what we think of as just traditional large language model sort of text AI?
Exactly, indeed. There are two levels of difficulty. One is people need high resolution images. So you not just predict a word, a few tokens, but you are
Hmm.
predicting the pixel wise, like the whole image, like a high resolution 4K image. That's a lot of pixels and a lot of tokens. So you need to generate the machine learning model to generate a lot of tokens
Hmm.
um, for high resolution image. And also for videos, you need to generate a long videos. And so that also add the complexity
Hmm.
um, to generate super long video, make it robust, make it no blurring. So a lot of token consumption. So we developed techniques called deep compression autoencoder
Hmm.
to shrink the number of tokens so that you need to generate less tokens,
Hmm.
trying to be lazy, but still you can recover it with very high quality.
Yeah, that's interesting. Social media is rife with these now kind of artificial videos and people debating whether it's real or AI. And it's sort of horrifying to think of using tons of energy to, generate cat videos, for example. And, so the way people use I think they don't think at all about energy consumption or compression. They just want to do what they want to do with it.
Right. Actually, there's a huge opportunity to make it more efficient by leveraging the nature of video, temporal similarity, and
Yes,
also the spatial similarity. We can get rid of tons of compute by using that, called sparse attention.
I see.
You don't attention is all you need, but you only pay attention to where you need. You
Yes,
don't need to pay attention where you don't need, or it's redundant, and
yes.
that can save a lot of energy.
Yeah, no, very interesting. So, besides consuming less energy, what are some of the advantages of these sort of lighter weight AI models?
Yeah, so it's not just saving energy, but also improving the productivity and revenue. For example, data
Mm.
center
Hmm.
is usually having a fixed power budget, right? And the more compute you can squeeze given this fixed power envelope, the more
Yes,
productivity, the more intelligence you can generate, the more tokens you can generate, and the more revenue you can generate, the more users you can serve. So
yes,
it's also productivity.
yes,
And also, once the efficiency is beyond a threshold, you can realize real-time AI. For example, you don't need to wait the AI to give you the information offline, but you can interactively
yes,
experience that. Example is NVIDIA's DLSS, deep learning super sampling. You
yes.
can do real-time translation from a gaming style video to a like real world like
I see.
video.
I see.
So this kind of real time is a very good point when the neural network is getting efficient enough.
I mean, it sounds like you've been working on these things since you were a graduate student, and I'm just curious, are the capabilities that we're seeing emerge surprising to you?
Yeah,
Had you anticipated this level of progress and pace, or are you also amazed, as I am, about the capabilities of these systems?
I'm pretty amazed. Thanks to the scaling law, right? Since 2022, ChatGPT moment, it was a lot different with this generative AI compared with before that. I did PhD in 2012.
Hmm.
That's when AlexNet just came. That's the first wave. And a decade later, since 2022, I think that's the second wave with the scaling law. People are squeezing a lot more intelligence by training on a much larger amount of compute, much larger amount of data, and the result is just so astonishing.
It really is amazing. It's exploded. What do you think the most sort of exciting capabilities are that have emerged in the last couple of years?
I think the most exciting thing is the self-reflection capability,
Yes.
the post-training capability, and the reasoning capability. So previously, pre-training is like you train a student till college, right? And after he go to find a specific job, he needs specific training, right? So we can do post-training for alignment, and also do this supervised fine-tuning followed by reinforcement learning to inject new paradigm and new to align their system, right? To get a lot of new knowledge in a specific domain. And AI these days with the test time scaling, I think that's a very cool feature since GPT-4o, where you can just increase the compute at the inference time and then it can do self-reflection to verify whether the previous generated result hallucinate or is true or not, and self-reflection and do continued generation. By scaling the inference time, the inference compute, the accuracy could be increased a lot. I think that's very exciting milestone.
It's so interesting because I think the average user begins to forget that they're not dealing with a person. And, that these AIs now have different personalities, different modes of interacting with the environment. I realize that that's a illusion in a way, but I think it's definitely influencing people's perception of AI and what they can do with it.
Yeah, those are all thanks to post-training.
Yeah.
So that you can align the AI with different characteristics.
Exactly. So you've actually been working now to make things run faster, more efficiently, et cetera, and potentially, on a variety of devices. So what's the impact, for instance, of, my now being able to pull out my phone and run AI on my phone as opposed to, having to either sit in my office or before that to be someone who had access to, large computing resources?
Yeah, I think in the future it will be a hybrid mode. Some super gigantic, powerful AI will sit in the cloud,
Yes.
in the data center. In the meantime, there will be a bunch of smaller language models or generative models sitting on mobile devices. They can talk, they can interact, depending on our prompt. If it is simple enough, the local device would be capable enough to just give you real-time answer. And if it is more challenging or more difficult, it will be routed to the data center and get it back. We'll see a lot of on-device AI scenarios, latency critical scenarios. For example, self-driving cars or robots. These physical AI applications, they need a real time. They need very robust, doesn't rely on the internet.
But really miniaturized.
And miniaturized
Yes.
with a fixed power budget. You
Yes.
don't want a whole trunk of computers sitting in the trunk. So that's where I think efficient AI is very critical.
Do you think there's going to be, just as we're talking, I'm thinking, do you think there's going to be a sort of market for much more specialty small models that can operate quickly? So, for example, if you go on to, any of the generative AI models, you can do very extensive travel planning. I can imagine very small, fast, sophisticated models that are marketing direct to consumer, for example, just for planning trips or, just for asking medical questions. I guess some of that is emerging, but do you think that's going to become more common?
Yeah, that's vertical AI.
Yeah.
And once you focus on a very specific domain, you can make it very focused and shrink it to only what is useful without having to have a lot of redundancy, and that give opportunity to make it very dedicated, very specialized, while being super efficient.
Yeah, no, it's interesting. So, you focused a little bit on making AI handle long documents or long videos very efficiently. What kind of things might that unlock for, everyday users? How would that help me, for instance, or one of our listeners?
Yeah, we did some long context work, such as streaming LLM. So our natural world is long context. Like we have tens of years of memories and very long textbook cover the whole semester.
Yes.
Or hour-long video, or a whole year of emails we may want to reference.
Yes.
So our world is naturally long context. And having the long context capability is difficult from the computing perspective because they occupy a large amount of memory, very slow to index, to search, to locate. And very interestingly, conventional large language models suffer from the loss in the middle issue. Can remember the beginning very well, the end very well, but in the middle tend to forget about it. So we propose a few techniques, try to shrink the memory consumption while be able to memorize very long document and continuously provide the interaction without having the memory to explode. That work is called streaming LLM. It's now part of the OpenAI's GPT OSS, open source version of the GPT model. Very helpful technique.
I mean, we've all had the experience, I guess, of you've watched some long video or read some long book and you're like, I know there was a scene or a piece of information that conveyed this, but I could never find it again. So I assume that, in terms of people processing large amounts of information, seeing something very long, that those kinds of things will also help, in speeding up data location, processing, etc.
Exactly. For
Yeah.
example, in a car, you want to prompt it, when did I hit another pedestrian? For example, you just
Yeah, I hope
locate,
I never want to process that,
yeah,
but okay.
you just want to locate a specific event that happened, like in your home. You want to see, did someone leave a package at my home?
Yes.
When did that happen? Right,
Yes.
I can locate that for you.
Yes.
And it's continuous interaction, and maybe finding the relationship between two different events.
Yes.
They might be long time apart from each other, but
Yes.
if you can understand them, the whole video as a whole,
Yes.
that can need, enable such applications.
That would save my husband and I a lot of conversation during TV shows saying, what did they do? Who were they again? It'd be nice to be able to figure that out quickly. I'm just joking.
Yeah.
That's a trivial example. But, um, so you've developed these AI model compression techniques that have already been downloaded millions of times. And what does that kind of adoption mean for the field? I mean, are the users leading to iteration for you? Are you getting feedback from all of the folks that are using these compressed models?
Right, that's a good point. Like our 4-bit LLM quantization technique called AWQ has been downloaded more than 60 million times.
Wow.
Not only from academia but also industry. Like
Yes.
NVIDIA, a lot of companies have integrated them into their products,
Yes.
and that means efficient AI is not just good to have.
Mhm.
It's a must have.
Yes.
So we need to think about, as neural nets continue scaling up, the efficiency demand would just be more important and can
Yes.
unlock a lot of capabilities. And we get a lot of feedback from our industry like NVIDIA, and we can continue to iterate on these
Right.
algorithms.
And they tell you what they'd like to see, presumably.
Yeah.
Yes.
For example, extending from a language model to visual language model.
Mhm.
That's a good example for that.
Yes. Yes. Yeah, that's really interesting. And you do you think, you mentioned about small devices linking to huge cloud servers, but presumably, the ultimate, you mentioned things like self-driving cars, et cetera. Ultimately, I might be able to own a phone that has everything it needs in a contained way. And I think that addresses one of the concerns a lot of people have, which is about security and AI. You know, you can glean a lot from an individual by the kinds of questions they're asking to
Yes,
generative AI.
absolutely.
So how do you think about that? Do you think as you build these models, do you think about how secure they are and, how they might be used for less than salutary purposes?
Absolutely. I think as the AI model are getting to multiple modalities, people have a bigger demand for privacy.
Yes.
Like they are listening to you, to your meetings, and looking at your uh, cameras, and having your reading your emails and notes, right? We want those information to stay
Right.
local. Nowadays, we see these 3 billion parameter, 7 billion parameter model are getting very capable from the algorithm perspective.
Yes.
And these silicons, these chips are also getting more powerful. Even mobile chips, they can run these 3 billion, 7 billion parameter in real time without problem. So I'm very optimistic with co-design software and hardware co-design to bring the gap smaller and smaller, so that in one day we can have a lot of applications running local and helping
Yes.
people solve the privacy concern.
Yes. So, it's interesting. How do you conceive of these things day to day? So, what does your day to day work look like when you try to approach these problems? I always like to sort of give people a feeling for like what the actual work you do looks like. So, on a day to day basis, how do you operate? What are you trying to achieve in small pieces to kind of make a larger successful compressed model or smaller compressed model?
Mm-hmm. We usually approach this problem from different angles, perspectives. One angle is software and hardware co-design. Um, we will think about which is a model or algorithm problem, which is a hardware or system problem.
Uh-huh.
For example, 4-bit quantization algorithm need to be coupled super well with the 4-bit inference kernel libraries, CUDA code that complement or implement those algorithms. So that's one angle. The other angle is the training and inference. Which technique should we target for training, accelerating the training, which target the acceleration of inference? And these days we see more demand for efficient inference, which is a good sign which means AI models are not just sitting in the lab for iteration, but actually going to mass production. So inference optimization demand is even bigger. We also look at different applications, the generation versus understanding. So generation means we can generate a lot of images, videos. Understanding means understand images and videos and see what's happening. And they can help each other by using the understanding model to label the data feeding to the training of the generation model. So these are the synergies between these perspectives. We also look at different technology perspectives. For example, sparse versus dense, high precision versus low precision. There's a very large design space, and I think the key thing I think day to day is kind of co-design, right? Opening the whole space as if you have the complete freedom in the ecosystem, what you can do to make AI more efficient, from training to inference, system to algorithm, hardware to software, generation to understanding, put them all together, unlock the space, and just let your imagination soar.
It's interesting. I think probably, a decade ago when we had students come to MIT, they felt that they could just learn to code and get a great job. And, what you're describing is, expertise in software, expertise in hardware, understanding of the context in which the AI, for instance, is going to be operating, et cetera. So what do you advise students who are sort of thinking about entering this area now? Like, how should they be thinking about what they need to know to operate successfully in this area?
Yeah, I think it's a great moment to rethink about the education and teaching and what students should learn. 80 or 90% of the coding during our day-to-day research nowadays, we find AI tools can do it super well. Well, some fundamental connection to connect different concepts together, and the design space exploration to know what are the possibilities. And I think that's something newer students should know. Not only algorithm, not only how to train models, but also the systems, the kernels, how hardware actually implements this stuff. AI is a very special animal where it's not a fixed workload from the computing perspective. It can be dense, it can be sparse, it can be full precision, it can be quantized. And there's just so many co-design opportunities, which means make it more important to learn the whole stack from computer architecture to operating system, high performance computing, compilers to machine learning to artificial intelligence, from NLP to vision. So this whole stack, I think they are getting tighter and tighter.
Yes. So what someone needs to know to really operate, fluidly within the space, in some ways is getting larger. Even if we think about, I think sometimes people think about AI in education, oh, we have to know a lot less because the AI will do it for us. But in reality, if you want to work in this area, you have to have a much deeper understanding if you're really going to be creative.
Exactly. Having the capability to connect the dots. And for each dot, AI might be able to do it very well or deeply.
Exactly.
The capability to connect the dots across design space, I think
that's really interesting. You're talking about teaching. Can you talk a little bit about your teaching platform, Efficient ML.ai, and tell me a little bit about it and actually what motivated you to start this effort?
Oh yeah, I have to. I initiated this Efficient ML.ai course 3-4 years ago. Try to disseminate the knowledge on efficient AI. Many companies are actually using that as a training tutorial for onboarding new employees. To deploy models. Because I see the huge demand for efficient AI and deployment from the cloud to to the edge, but there's a big shortage of such talents. So we want to disseminate to more students,
Yes.
equip them with these capabilities. Some of the students now are in like large companies. Some of them are become a professor. Some of them also initiate their own companies, and I see it's getting very fruitful these days. We'll continue that effort, make it public. All the lecture materials and videos, our slides are all public and everyone can access.
What do you think about the sort of industry, academia? I wouldn't even call it divide. It's not really a divide, but the different contributions that industry and academia are going to make to the future of AI. What do things look like 10 years from now? Are we still doing deep levels of AI research in universities? How are we collaborating with all of the companies that are emerging? How do you think about that?
I think companies offer lots of new problems and also offer lots of crucial resources. Like I'm very thankful for NVIDIA donating us the GPU cloud compute resources. Jensen Huang, very ambitious and very innovative, and that impact our research a lot. And I think for academia, we have a lot of freedom to explore different like crazy ideas, going to 4 bits or even 2 bits.
And
making 99% sparse, all zeros. Those crazy ideas, we can explore them and get it open source and contribute back to industry. And I think this relationship will just getting tighter and getting more fruitful.
That's great. That's great. So what do you do outside of this? Do you have hobbies? Do you tell me a little bit about things besides AI that you find of interest?
Oh yeah, there's a coming ski trip with our lab. Lots of fun activities.
Downhill.
Ski at the speed of GPUs.
I'm more of I guess that explains a lot, because I'm more of a cross-country kind of analog skier. Nice and slow and flat.
Yeah, it's fun, especially in Northeast.
Yeah, very fun, very fun. And for listeners that really want to understand a lot more about AI beyond sort of the headlines, where do you think they should start? In other words, how do people understand a little bit more what tools are available to them, how they might use them, how they might think about them, how they can use it in their own lives?
Yeah, I think these days there are so many great tools. Just get hand dirty and try a few tools, get hand dirty and try the tools. And then use the tools, write the code. Start implementing stuff. Or take the efficient ML lectures. And we have lots of hands-on projects. Like after doing the projects, basically you can deploy a 7 billion parameter model locally on your laptop.
Oh, really?
By completing the course.
Wow, very cool. Very cool. Yeah, no, I think the future is going to be very interesting in this regard. And, I don't do AI research, obviously, but I've started using the tools, and they're really quite amazing. And I think people would find ways to make their own work better, kind of allaying some of the fears of AI replacing what they're doing, but actually using AI as a extender of their own creativity.
Yeah, absolutely. AI for science, I think there's huge momentum.
Exactly. Well, this has been very enlightening to me. I'm sure our audience is going to love hearing all about this, and you're going to get more than 60 million downloads, I'm sure, as time progresses. And so I want to thank you for joining us. And I want to thank our audience for listening to Curiosity Unbounded. I very much hope our audience will join us again, and I very much hope you'll join us again. So I'm Sally Kornbluth. Stay curious.
Thank you, Sally.